Okay, so we're very happy to have Mauro di Nasso from PISA back to give part 2 of his talk on non-standard natural numbers and arithmetic Ramsey theory and topological dynamics. Go ahead, Mauro.
Okay, thank you. And thank you twice for asking me to give a second part of this seminar. And it will be a bit disjoint from what I told the last time, although there are, of course, common parts. In this part, I will focus mainly on topological dynamics in a non-standard setting. So last time I talked about aspects of arithmetic Ramsey theory, and I introduced the non-standard natural numbers of non-standard analysis, sometimes called hypernatural numbers. And then I gave a proof of Heinmann's theorem and of Ramsey theorem by using this non-standard setting. But this time I will focus on topological dynamics in the hypernatural numbers. So the hypernatural numbers can also serve as a setting for dynamics, discrete dynamics, and we will see how to do this. And in the second part, I will present some new result about monochromatic infinite patterns in the integers. So we will switch back to the topic of Ramsey theory. Of course, please feel free to stop me whenever you need to ask questions or in case you need more details. Okay. So let me remind you this basic theorem in this area. It's named after van der Waerden, and it says that this is a typical result of Ramsey theory. We discussed this last time, but let me remind you this theorem. In every finite coloring of the natural numbers, meaning in any finite partition, one can find arbitrarily long monochromatic arithmetic progressions. So in one piece, we will find arbitrarily long arithmetic progressions.
Mauro, sorry to quickly ask a question out of curiosity. So that's exactly as you said, that there is one piece that has arbitrarily long arithmetic progressions, not that they can occur in different pieces.
No, in the same piece. In the same.
There is one piece that has arbitrarily long.
Yes.
But they can be of different colors. Or they probably are of different colors. Right?
Well,
no, that's just what I mean. But if there is one that has arbitrarily long, why doesn't have an infinite one?
No, there is one color, right. And in that one color, you can find arithmetic progression of arbitrarily long size.
Oh, I see, but they will be different arithmetic progressions.
Yes, of course.
Right. No, I understand now. Right. The
van der Waerden theorem.
Right, that's right, exactly. Right.
The property with infinitely long progressions is I mean, it would be false. I mean, you can find a partition in two pieces of the natural numbers, none of which contains infinitely long arithmetic progressions. So okay, it's important to have only finite progressions, but of arbitrarily long length. So the proof is not simple, it's a nice combinatorial argument, but it really is a clever one. It takes, I mean, it's not trivial at all. But as I say here, the density version of this property, and sometimes in Ramsey theory, people consider the corresponding density property. In this case, it's much more difficult. And usually it is always the case. So what is the density version? It means that you want that property in any set of natural numbers which is large. So here large means having positive upper asymptotic density. Now I recall this notion last time. It simply means that if you take a set of natural numbers and you want to give a sort of measure about how large this set is, you could count how many elements from A you have up to n and divide by n, and then you take the sequence of these relative densities, and the upper limit of these is the upper asymptotic density. In case this density is positive, then Xenoradic proved that the set contains arbitrarily long arithmetic progressions. So of course, this is stronger than van der Waerden, because in any finite partition, one of the pieces must have positive upper asymptotic density. And this was a really strong result. And in fact, the words "a masterpiece of combinatorial reasoning" is the way that Terence Tao described this theorem. Okay, let me just go quickly, and let me mention that there are also alternative proofs of this theorem. I'm telling you just for curiosity, have been found later by Fürstenberg using ergodic theory, and that was a breakthrough because it was a novelty that the methods of measure theory and ergodic theory could be used in this area. And then more recently by Timothy Gowers using Fourier analysis. And in fact, Fürstenberg developed an area of research where one uses ergodic theory in combinatorial numbers. Now there is still, let me just mention this. This is probably the most important open problem now. And it says that if a set is large enough so that the series of reciprocals diverge, then it must contain arbitrarily long arithmetic progressions. Now this conjecture is still open even for arithmetic progressions of length 3. So of course, if a set has positive asymptotic density, then the hypothesis is satisfied. But there are sets of with zero density, for instance, the set of primes, that are still large enough so that the series of reciprocal diverge. And in that particular case, this theorem was proved by Green and Tao in 2004. So the sequence of prime numbers contains arbitrarily long arithmetic progressions. This was a celebrated result. But the point is to understand if this property only depends on the largeness of the set or depends on the structure. In this case, of course, in the proof of Green-Tao theorem, peculiar properties of the prime numbers are used. But the conjecture is that any set of that size must contain arbitrarily long arithmetic progressions. And let me mention that just a few weeks ago, Randy and Jean announced a new proof of Xenoradic theorem by non-standard methods, and I'm really curious to go through that proof, because all proofs of Xenoradic theorem are really difficult to understand and really long and complicated. So probably Randy and Jean found a way to simplify a bit the arguments by using non-standard methods. Okay, all of you know about non-standard analysis. I mentioned this in my previous talk. Let me just repeat a couple of slides just to remind what we mean by non-standard analysis. Essentially, we are considering elementary extensions of the objects we are interested in, and such elementary extensions are taken in a uniform way, in a sense that you have a whole universe of objects of which you can consider this extension that is called non-standard extension. And this is done in such a way that the transfer principle holds, meaning that whenever you have a first order property, because elementary property means first order property, that property holds for objects A1, AN, if and only if the same property holds for the corresponding hyperextensions. So in model theoretic terms, the hyperextension will be a complete elementary extension, meaning an elementary extension with respect to the complete language, the richest possible language, first order language that you can consider on a given set. And typically, in non-standard analysis, people consider the hyperreal line, so the non-standard extension of the real numbers, because there one finds infinitesimal numbers, infinite numbers, and those are useful to develop, say, calculus, and starting from that, one develop more advanced topics. But here, in combinatorics, one focuses on the non-standard version of the natural numbers. So you can simply think of the hypernatural numbers as an elementary extension of the natural number with some strong additional properties. Okay, now let's go more directly to the topology here, because we want to perform topological dynamics. Now, there is a natural topology that one can give to the hypernatural numbers. And in general, one could do the same with any hyperextension of any structure. But here we are interested in the hypernatural numbers. Now, this is called the S topology, meaning the standard topology. And this is a classic notion of that was considered since I think the 70s or even before that, starting from Robinson himself. And one takes as a base of open and closed sets the hyperextensions of subsets. So in model theory, one has a corresponding notion. I think it is called the logic topology, but I'm asking Roman if this is correct. I read somewhere about this logic topology, which is a way to give a topology on the set of complete types.
Well, it's a known topology, but I don't know who uses the name logic. Maybe Carl knows.
I think I read this logic topology, but I'm not sure.
Right. It could be.
In any case, I mean, this is of course a natural topology one could also consider in general in models of theories by considering this topology on the complete n types. Now we have this topology. Oh, Lord, okay. On one side. And then we have another object that we discussed in the first part of my talk, the Stone-Check compactification of a discrete space that can be characterized as the space of all possible ultrafilters on the set X, and where, again, a base of open and closed set can be given in a natural way by considering the families of all ultrafilters that contains some given set A. Of course, there are strong similarities between the two objects, the two topological spaces. And let me mention that the Stone-Check compactification, for instance, of the natural numbers, that is the object we are interested in, is the largest possible Hausdorff compactification of the discrete space N. And this statement can be given a very precise meaning. Now, the hypernatural numbers, in some sense, they are an even larger compactification. Of course, we lose the Hausdorff property, so compactness is still there, provided one assumes saturation. But on the other hand, one is losing the Hausdorff property of the topological space. But the nice point is that the hypernatural numbers, since they are an elementary extension of the natural number, they have nice algebraic properties that one can use. And indeed, one uses such properties in combinatorics. So all these properties are easy to prove, not all of them actually, probably the third one takes a little bit of time, but they are the basic properties of this topological space. So we have a compact space, and this is a consequence of saturation, or as we say in non-standard analysis, of a weaker property that is called enlargement property. In any case, we assume that we are working with a sufficiently saturated model. So this star n is compact. It is completely regular, meaning that you can separate closed sets and points by means of continuous functions that take only values 0 and 1. But the space is not Hausdorff, as I mentioned before. However, it is a compactification in the sense that N is a dense subset of star N.
Mauro, a quick question.
Yes?
Is there a simple example of non-Hausdorffness? Why is it not Hausdorff?
Well, there is let me mention, I was about to mention this result, but let me, the problem of having the topology, the S topology on star N Hausdorff is an interesting problem because it is independent of ZFC. So in general, this space will not be compact.
I see.
How to explain this?
No, if it's complicated now, then let's not go there.
Can I say something quickly?
Sure, Karen, go ahead.
Well, typically, an ultrafilter, a monad of an ultrafilter has many elements, and two different elements in the monad of the same ultrafilter cannot be separated.
Oh, they won't be separated. I see.
And you have plenty because for the same, by using the same procedure that show you that one can find one point that generate an ultrafilter, you can easily find two different points that generate the same by using the same saturation argument.
I see.
So it is in principle possible, and in fact it is consistent that one has the Hausdorff property, but in that case, not all ultrafilters will be obtained by taking the non-standard points. We discussed this in the last talk, but I will mention this again. So let me just complete this list of properties. We have a compact and completely regular space. It is not Hausdorff, but N is dense in this space. And we also have a sort of universal property because any function from the natural numbers into a compact Hausdorff space can be extended to a continuous function in a canonical way, meaning that you take as the value in some, say, infinite point as the unique point of the compact space that is close, near to the image of the hyperextension of the function in the point. Now, it will take some time to explain this in detail, but this is part of the nice non-standard characterization of compact spaces. So I can, the non-standard characterization of a compact space is a nice one, I think, because it says that K is a compact space if and only if you pass to the non-standard extension star K, you have the property that any point in the extension is close to one of the old points in the starting space. Now, close, what does it mean here? It is written at the end of point 3. It means that the point belongs to the non-standard extension of all neighborhoods. So let me just mention one example. Consider the hyperreal line, for instance. Is the hyperreal line with the usual topology compact? No. Why? Because the non-standard extension star R, which is the hyperreal line, contains points which are not close to any of the standard points. Because if you take an infinite point, that will be infinitely apart from one of the old points. On the other hand, if you take the closed unit interval and you take the non-standard extension of this, then any point in the non-standard extension will be, in any case, infinitely close to one of the old real points, the previous real points of the unit interval. And why you need the interval to be closed? Because if you take the open interval, say from 0 to 1, in the non-standard extension, you will find positive infinitesimal numbers. And a positive infinitesimal number is not close to any of the elements of the open interval from 0 to 1, because a positive infinitesimal number will be close to 0, but 0 is not an element of the original interval. So along these lines, one can give a non-standard proof of the fact that a subset of the real number is compact if and only if it is a closed bounded interval. And this property can be generalized to any compact space. But you don't need this in the sequel. I mean, I'm mentioning these properties because they are part of the nice property of star n as a compact space. But we only need to know that the space is compact and completely real. Point 4 simply says that since we are working with non-standard analysis, we have a nice way to extend functions by taking the non-standard extensions. And in that way, we obtain functions with the same elementary properties. Okay, let's go. No, not okay. This is what I mentioned last time, that any number generates an ultrafilter in the non-standard setting. And that is the definition. And this corresponds to considering the one type of that element. Now, here we are working with the language that contains a symbol for any unary relation. So any subset is definable, and in this way, the one type here is exactly an ultrafilter. So since we are assuming saturation, we obtain in this way all possible ultrafilters. And the same ultrafilter is obtained many times. So we don't have the Hausdorff property. Okay, and it is a general fact in topology that in case a space is not T0 even, one could consider the Kolmogorov equivalence. So you can say the 2 points are topologically indistinguishable if they have the same neighborhoods. Of course, this never happens in the Hausdorff case, but in this general, more general setting, we can have this. And one could consider the quotient space called the Kolmogorov quotient. Now, all these things, of course, are related, because last time we defined the notion of U equivalence, which is the same as to say that 2 points generate the same ultrafilter. They are indistinguishable. And this precisely corresponds to be topologically indistinguishable in the S topology. This is not a theorem, it's just reading the definitions, and they are equivalent way of describing the same notion. So the fact here is that the hypernatural numbers have a Kolmogorov quotient that is precisely isomorphic to the Stone-Check compactification. So these two objects are closely related. In this sense, I was saying that star n is an even larger compactification, because a quotient of that is the Stone-Check compactification, which is in turn the largest possible Hausdorff compactification. Okay. Let me mention these open problems that can have some interest. And I think also Karel Bacek at some point found some constructions about these Hausdorff ultrafilters. I don't know, Karel, if you at some point wrote down a paper about those constructions. I remember you did some example in Omega 2.
No, I think we found that all these results I got were known already.
Ah, okay. Okay, so the possibility of having a Hausdorff space by considering this S topology is equivalent to the existence of these ultrafilters that one naturally can name Hausdorff ultrafilters. And in set theoretic term, the property is written there, provided you are familiar with the notion of image of an ultrafilter under a function f. In any case, it is a consistent property with ZFC, but it is not known today if these Hausdorff ultrafilters can be proved to exist in ZFC. Okay. And this yes.
Also, can you remind me what complete means here?
Complete elementary extension means that you have an elementary extension with respect to the richest possible.
Oh, the full language.
Yes.
I see. Right.
Of course, if the language is countable, that's a different story.
And so I don't know if you had a chance to take a look at it, because for just the modest language of PA, there are those constructions of Abramson and Harrington of models without indiscernibles. Okay. And there is a technique one can try, but I wonder how much it depends on the language. Have you looked at it? Have you?
No, but I'm pretty sure that it much depends on the language, because just as a curiosity, this property was announced as a theorem, I think 15 years ago or something, by Shelha and Bartoszynski. But eventually they found a mistake in the proof. So it must be, this is, to me,
means
that it must be really difficult.
No, it probably is, but even those Abrams and Harrington results they rely on some heavy Neschetschul-Redl kind of combinatorics. So there's nothing simple about it. But there are some natural simple constructions just for models of P. Julia Knight had one, and one would just have to look at how much it depends on the
So the result is that with a countable language, you can find.
Well, so there are constructions of nice constructions of large models like of cardinality Aleph1, such that every two elements realize different types.
Oh, so, okay. It's exactly this kind of property. Yes, I will. And so
maybe
you can send me some reference.
I will. For models of PA, and Attar also knows about it. That it relates on this possibility of creating the super minimal extensions. So somehow you have already a large model, a large countable model, and you elementarily extend it to one that's generated just by a single element, and you keep doing it. But it's a countable language really, because we want to have those countable models on the way all the time. Anyway, but this is something certainly to take a look at. I'm sure someone has, but.
Yeah, so just to jump in here, I think that none of those would really translate to the complete language, right? None of those techniques.
Right, not right away, but there were also some theorems of Glass related to minimal extensions of the full language. Some old work that actually preceded the PA versions of the results. So maybe there is some connection, because there was a connection to constructions of various kind of ultra filters. But you're right, as is, they want. Anyway, so something to take a look at.
Yes, it is worth having a look, because sometimes these ideas, they can be translated in some form. Some others cannot, but some can be used even if in this set theoretic context. Okay, I will have a look. So let's finally go to the definition. Let me remind you the very basic notion that we need from topological dynamics. We just take the simplest possible case of a compact space and a single continuous map from the space into itself. So this is already a topological dynamics. It's discrete because we are considering iteration of the same operator, of the same continuous map. So we are applying this, say, T again and again. So you start from a point X and you have the orbit. So you take T of X and then T of X and so forth. And we have the notion of return set of some point X in a neighborhood. So that is the collection of all K, so that the kth iteration of T at X belongs to the neighborhood. Okay, these are the two basic notions that one can use. And here we can, this is not the only possible dynamics from a non-standard point of view, but it's the simplest one, and it already gives nice results. And it is the shift operator. You just take the function +1, and that is continuous. So you have a continuous map on a compact space. So you have a dynamics. And the orbit of a point is simply the collection of all finite shifts of that point. Okay, all these notions make sense in any, say, model of Peano arithmetics, for instance. Now, a central notion in topological dynamics is the notion of recurrent point. So what is a recurrent point? It's a very special kind of point that have the following property, that for every neighborhood, you wait some time and after, say, k many iteration of the operator at x, you will go back to the neighborhood U. So here, natural numbers, I assume that we are starting from 1. So we are taking either t of x belongs to the neighborhood, or t of x belongs to the neighborhood. One of the finite iteration of t must bring the point x again back to the neighborhood U. In our context, where the basic open neighborhoods are just the non-standard extension of subsets, is given here. A point is recurrent means that in case this point belongs to star of A, then Ni plus k, which is the kth iteration of the shift, must again belongs to star of A for some positive integers. Now, for instance, you can immediately translate this in a model theoretic language, for instance, in a model of Peano arithmetics, by saying, if you have a point that satisfies some property phi, then there must be a finite k so that also the point plus k satisfy the same property phi. If this happens for all possible properties phi that are satisfied by the point, then the point you can call the point recurrent with respect to this dynamics. Let me mention what we discussed in the last, in the first part of the talk, where I consider a point that is in some sense self-recurrent. So of course, this is not a notion that makes sense in general, but in topological dynamics, but here it makes sense because one could ask for a shift which is given by a natural number A, which itself belongs to the given set A. So we're just not asking for a shift of the point Ni, but for a shift by a natural number which belongs to A. And these kind of very special points are precisely corresponds to the idempotent ultrafilters. And we saw last time that these idempotent ultrafilters are central in Ramsey theory because by using them, one can prove Heinmann theorem, and starting from that, one can prove many other more general properties. So in some sense, even idempotent ultrafilters are a sort of recurrent points of some special form. And I remind you the statement of Heinemann's theorem. It says that given any finite coloring, you can find an infinite sequence. This is a really strong result with the property that all possible sums of finitely many elements taken from that sequence belongs to the same piece of the partition, are monochromatic. And you can prove this theorem, and we show that in the first part of the talk by using these self-recurrent points that corresponds to idempotent ultrafilters. Okay, so now we go to the next level, which is the definition of uniformly recurrent point. And indeed, in order to prove the existence of recurrent point, one uses this stronger notion. This is sometimes happens in mathematics. You want to prove something, but in some sense, it is easier to prove something stronger. And here, the right notion seems to be that of uniformly recurrence. So what does it mean? We want for every neighborhood, we want to go back to that neighborhood after a finite number of iterations, but we want to do it several times. In the sense of syndeticity, syndeticity is a notion that comes from topological dynamics. And the definition is the following: a set of natural numbers is syndetic if it has bounded gaps. It means that there is some n, which is the largest possible gap that you have between two consecutive elements of the set B. So for every n, either n or n plus 1 or n plus 2 or n plus plus 3 or at most n plus big N must belong to B. So you have only bounded gaps. There is a largest possible size of a gap in the set. So this means that you want to go back to the neighborhood in a bounded time, because here time is discrete. You can think of time as the number of iteration of the operator T. So the definition is, in the context of the hypernatural numbers, the following: a point is uniformly recurrent if the return set is syndetic for every neighborhood of the point, which means for every A, so that the point nu belongs to the non-standard extension. So again, this notion makes sense in any, say, model of Peano arithmetic. A point is uniformly recurrent is if whenever the point satisfies some property phi, then the collection of all finite k, so that the point ni plus k also satisfy the property phi, form a syndetic set. Now, the nice point, and this is the basic of topological dynamics, is that there are always such points. And one proved that by using zone lemma, because the step is to find minimal subsystems. So you see, ultrafilters are maximal objects, and you prove their existence by using zone lemma. And here, almost with the same procedure, in some sense, you use zone lemma to prove the existence of minimal subsystems. Of course, here, the property of compactness is crucial. Minimal, so every point of a minimal dynamical system, and this can be proved, and of course I'm not going into details here, but they are very basic results and not difficult to prove. Every point of a minimal dynamical system is uniformly recurrent. And the point here is that although our space is not Hausdorff, the point here is that we know that the space is regular. So all you need to use the same proof is to have X compact and regular. And star n is completely regular. So we have the property that in the discrete dynamical system of the hypernatural numbers, one always finds uniformly recurrent points. Now, I'm late already, so let me mention that one can prove by using uniformly recurrent points in star n van der Waals theorem. Because the property that one can prove is the following: if we take any uniformly recurrent point of star n, and if you take any neighborhood, meaning any set A so that ni belongs to star A, then the return set contains arbitrarily long arithmetic progressions. So you see, you can formulate this for any model of Peano arithmetics. You could say, take one of these very special points, take any property phi satisfied by this property, then you have that the collection of finite numbers n so that ni plus n satisfy the same property is a collection of natural numbers that contains arbitrarily long arithmetic progressions. And I think this is a nice result. The point is that the existence of uniformly recurrent point is a really basic fact of dynamical topology, and one can prove that simply by using zone length and the compactness property. I don't think I have the time to go through the proof, but let me show you how this theorem, the fact that the return set contains arbitrarily long arithmetic progression, how one can prove from this theorem van der Waals theorem. And one do like that. So you fix a uniformly recurrent point. Now, for every finite coloring, you take the color with the property that that point belongs to that color. Of course, this is clear. You take the color that contains that recurrent point. Now, by the theorem that I mentioned before, the return set, meaning the collection of all n in the natural numbers so that nu plus n belongs to this star C, this color, we know that this contains arbitrarily long arithmetic progressions. What does it mean? It means that for every k, we can find a progression of length. In this case, I think is k plus 1. In any case, you have a plus d, a plus 2d, and so forth, a plus kd, that belongs to the return set. And this is the same as to say that nu plus a plus d, and so forth belongs to star C. Now, we proved the first order property for any fixed k, that there exists element x, a, and d in star n that form an arithmetic progression inside star C. And then by elementary equivalence, by transfer, we say in non-standard analysis, the same property holds for n. So we find the existence of a arithmetic progression in C of length k plus 1. So you see, we can translate the property of return sets in this topological dynamics back to the natural numbers. It's late. I'm not going to the proof. I can give you the slides if you want, but let me just mention that the proof is 1, 2, 3 slides. That's the proof. It's a proof by induction. And you should compare this with the standard usual proof of van der Waals theorem, which is way more involved and complicated. Here we use the fact that we are working with the natural numbers and that the neighborhoods are extensions of sets of natural numbers. So topology here is strongly mixed with arithmetics. And there is, if you have questions, we can go through the proof if you want. Yes.
I have a question. May I go ahead?
Ahead here.
Yeah. The question I have is naive. In Ramsey theory, people have looked at a recursion theoretic form of Ramsey theory. So one might ask along those lines if the initial partition into different colors, C1 through CK, is given recursively. So those are, recursive infinite sets. Is there a recursive function which, given the length of the desired arithmetic progression, gives you the starting point? In other words, actually computes the specific starting point for the arithmetic progression. So say if you want the arithmetic progression to be of the form a plus bi, something like this, given a and b, the recursive function will stipulate what this, given b, the recursive function will stipulate what the starting point a is.
I mean, I understand the kind of question you are asking, but here we cannot have a control on this.
Yes, that's my whole point. That this, although it's a very elegant approach toward van der Waerden's proof,
yes, it's because we are using Zorn lemma right from the beginning to find this uniformly recurrent point. On the other hand, we are taking arbitrary finite partitions with no recursive properties at all. If you want to pay more attention to this, you should go through the original combinatorial proof. This is typical of this kind of combinatorics. When you use non-standard methods or ultrafilters, you lose this idea of explicit constructive thing. On the other hand, let me mention that there are, I saw some work in a topic called proof mining, that by starting from this kind of non-constructive proofs, let's call them in this way, they were able to find explicit bounds and explicit values for the patterns, monochromatic patterns that one finds in Ramsey theory. So there is a way, although everything looks really non-constructive, to extract some information also in the sense that you were asking. I don't know anything about this.
Okay, thank you.
And in the way it is written here, there is no information that I can give you.
Okay, thanks.
But on the other hand, this is not completely non-constructive as it looks. Because although the starting point is non-constructive, there is a precise combinatorial argument that you can use. So some information I'm not able to do anything in that direction. And it's a different viewpoint.
Sure. Okay, thank you.
But there are people that are interested in these connections between this non-constructive thing and the constructive meaning of what you are doing.
Mauro, so can I ask an even more naive question? With apologies. Look, so now we know that van der Waerden's theorem is provable without any set theoretic assumptions. Okay, and so in a proof like that, suppose we didn't know a more constructive proof or elementary proof, would we have known the same? So if you have an combinatorial argument like that, suddenly you need a certain ultrafilter, and for that ultrafilter you need to assume the axiom of choice, some version of it. Is there something from the form of the theorem that you're using that tells you that you don't really need it?
Now I don't remember precisely, but there is a precise theorem of this kind. For instance, Heinmann's theorem that you can prove by using ultrafilters, it has a specific form. I think it's pt2 or something. I mean, if you can formalize the property in some way, which is not too much complicated, then if you can prove it by assuming V equal L, so you can assume the continuum hypothesis and you can assume the axiom of choice, then it is also provable in ZF without the axiom of choice.
Right,
This is a general result.
Yeah, right, so this is absoluteness.
Absoluteness result.
Canfield absoluteness theorem. Yeah.
Exactly.
Right. So for that, you
Karel
really
knows more than I do about this.
Right. No, this is something that everyone has heard at some point or the other, and I have as well. But it's interesting that it really depends on the syntactic form of the statement, and would be not necessarily on the content of what's being proved. You would think that there is some combinatorial content that, regardless of the number of quantifiers, there will be some kind of way to go higher than that. But Karel, do you know if anything that it's not like if you have something like sigma 1,3 that you for sure know that you need the axiom of choice. Sometimes you do, sometimes you don't.
Yeah, but I think these theorems are generally pi 1,1 or something like that. So,
I see.
Within the scope. They say like for every set on natural numbers or for every partition of natural numbers, something arithmetic happens. Right? So.
Right, but it's I was thinking of sort of that you go from the syntax of the theorems to some sort of semantics. That if there is some kind of a wise way of looking at certain kinds of theorems, that that you would have some transfer for that. But I guess it's too vague question to ask.
Yeah.
Okay, so it's too late already. So let me just quickly say some recent results that are about, and I'm slightly changing the topic. So Heinmann theorem was formulated with respect to the operation of sum. There is also the multiplicative Heinmann theorem. And there is a combination of the two things that was proved by using ultrafilters, by the way. I don't think, at least up to 10 years ago, there was no elementary proof of this property, that in any finite partition, you can find two different infinite sets, so that all finite sums from elements from the first set X and all finite products taken from the infinite set Y belongs to the same piece of the partition. So the same CI contains all these sums and all these products. But the point is that these X and Y are in general, could be disjoint. So the question is, can one have sums and products in the same piece of the partition that are taken from the same set? And this is a very interesting and still open question. For instance, if we want in any finite partition of the natural numbers, if we want to find A, B, A plus B, A times B that belongs to the same piece of the partition, this is an open problem. And it seems a really interesting one. And it seems we are close to prove that property, but still is open. So you see there are many close results that have been proved already. Oh Lord, it's too late. Okay. So I'm finishing here. I'm simply saying that I found several infinite configurations similar to Heinmann's theorem, and a particular case is the configuration here, A plus B plus A times B. This is partition ready. And I found other partition regular configurations of this form, by using strange, unusual associative operation of on the integers, because at the end, all the machinery used in the algebra on ultrafilter that was developed by Heinmann and Strauss, the starting point is an associative operation. All you need is the semigroup structure. And there are kind of strange associative operation that one can use. And for instance, let me just mention one. These ones are associative operations. So if you take the operation A star B to be A plus B plus A times B, that is associative. And also that those more general forms. And by starting from those operations, one can use ultrafilters, idempotent ultrafilters with respect to this associative operation, and prove the analog of Heinmann's theorem and other theorems in Ramsey theory. Okay, I'm really sorry that again I was late. Let me finish. I don't know if I mentioned this already, but okay. I'm curious to learn if these notions from topological dynamics can have some interest for people working in model theory, for instance. And on the other way around, if techniques of model theory could be used successfully to attack problems in Ramsey theory. Okay. Again, a commercial in case people are interested in this kind of combinatorial things. And a last advertisement is this one. So everyone is invited to this conference. We are crossing fingers for the next June. It was postponed 2 years already, so it was intended to be in 2020 and then 2021, and now we hope finally to hold this conference in 2022. Okay, thank you for your attention and sorry for being late as usual.
Thank you, and so thank Mauro again. And yeah, let's open it up. I know there were a lot of questions already, but if there are any other questions, let's open up for that now.
One thing, you were talking about the Schoenfield's absoluteness and its relationship to these issues. There was also, I mean, way back when, I mean, a step further in that direction, there was a theorem of Fenstad, I think it was, which showed that using Solovey's techniques for the measure problem showed that if something was provably delta 1, 2, then it was a measurable set. Okay, so maybe there's a way of getting absoluteness to work as long as you know what you are dealing with are somehow provable properties in ZF.
I have to say that most people that are actually working in combinatorics are not really excited about these absoluteness results because they are more on the constructive viewpoint. Some of them don't even want to hear about ultrafilters or these kind of things. But some other people are on the opposite. They are excited about these strange objects that can give you results. So I don't know what to say. I mean, of course, these absoluteness results are really nice and important. And I like them because they are a great bridge to tell you, to give you informations. But
Mauro, I have a very simple question. So in those last results that you mentioned about those new associative operations, do you use computer technology? Do you use software?
No. That's, I mean, I just, so you see, the starting point is, at the end, I just took these transformations, natural numbers. And then the point is to have the range that is multiplicatively closed.
Mm-hmm.
Because if it is multiplicatively closed, then you have a semi-group in the range. So it's closed under products, and product is a associative operation. And then you simply go back, and there is an operation that you.
Oh, in other words, it's something simply that you can check by hand. That's not something that would involve complicated.
Yes.
Okay.
At the end, the idea is completely elementary, but it gives nice consequences. So you couldn't tell at the first sight that this operation, say, L times AB plus K times A plus B plus K times K minus 1 divided by L. This is associative. I mean, I don't see it clearly, but you can check.
This is not really a question, but I just want to go back to the statement of one of the proofs that involved the term uniformly recurrent. I think it was it was a result that you used to prove van der Waerden, or sort of before we proved van der Waerden's theorem. Yeah.
This one?
This side, yes. Okay. I just wanted to see the statement of this theorem. Thank you.
Oh, so about this. So when you say that, I don't remember exactly how, but is this part when for the existence of uniformly recurrent points you need set theory?
Yes, you need zone lemma.
Right.
Because you need minimal dynamical systems.
So this is not something that pure model theory would give you.
It's not something, sorry, say it again.
That just pure model theory would give you.
Right. But since you have a compact topology, you can. Yes, it takes some set theory if you want, in some sense. Well, I don't know, maybe by using model theoretic techniques, one can try to prove the existence of this kind of special points. This, I don't know. Maybe there are similar notions that are more used in model theory that one can use.
Right, for us, it would be, for us would be something to take a look at, because I mentioned, when Atal mentioned about that in an uncountable language, many things are already, not really feasible for us in constructing certain models, because you need limit points in the construction and things become difficult. But it would be interesting to go back from this and sort of miniaturize this into the case of PA and see if there is anything interesting on the PA side about it. So it wouldn't help you to prove anything about topological dynamics, but maybe it would be something interesting on its own in models of PA.
Yes, I mean, if you are working with, say, a countable model, maybe you can, by some form of induction, try to prove the existence of this kind of points. Maybe it's can be done. No idea.
Right. That's
Never
interesting.
tried. And
So
here I'm taking the
we'd be
shift.
looking for
The shift is +1. You could take any definable function.
right.
As long as it is continuous, but it is with respect to the logic topology.
So you'd be looking for a model of PA with an element such that every first order property that is satisfied, like so that the type every first order property that is satisfied by that element is also satisfied by sort of something
Shift.
close.
Right.
Yes, that is recurrent point.
Right.
Right.
Yes.
Right. So is otherwise
And
inside
there should be a
A,
balance.
instead of A, you would have a first order property.
Yeah.
Yes.
But that's interesting.
It's almost a dual to the notion of rare type. Not exactly, but it's somewhat of a dual to that notion.
Right. It's closer to ubiquitous. We do have ubiquitous types, the types that are realized almost anywhere, and there are even those absolutely, and we could never find any applications for them. So Jim has constructed some. So maybe this is something to look at.
Is that in the book?
No, it's somewhere in Jim's note. Jim, there was a question about whether you want a type of an element such that if you take any and now as neighborhoods, you think about just intervals, infinite intervals in the ordered set of a model of PA. That in any infinite interval you actually find an element realizing it. They're really ubiquitous, and so they may be of some use here. So they will be even more.
In every infinite interval, you find something is the characterization, non-standard characterization of fixed sets, of synthetic sets.
I see. But no, so there is something that is right. So involved in it. Yeah. And I don't remember, but Jim proved it, existence of such, and perhaps he just used this notion of synthetic. I don't remember him using the word, but he might have used some combinatorics to prove existence of those.
Are there any other questions? Okay, so let's thank Mauro again. Thank you for coming twice and finishing most of your talk, which was great. So I enjoyed it. Thank you.
Thank you, Mauro. It was a very good talk.
Hello, everybody.
Good
Ciao,
stuff.
Ciao, Roma.
All right. Ciao, Mauro.
Ciao.